You ever see a figure skater start a spin and then whoosh, they just become a blur? Or think about a satellite just hanging out up there in orbit. How does that even work? Well, it turns out the answers are all hiding in the physics of rotation. And the cool thing is, we're not going to learn a bunch of brand new, complicated rules. Nope. We're just going to translate the physics you already get. I mean, seriously, you already know the basics, right? Pushing a box, throwing a ball, you get it. You push something, that's a force, and that something, which has some mass, starts to speed up. That's linear motion, straight line stuff. And believe it or not, that's pretty much all you need to know to get started. Okay, but what about things that spin? A wheel on a car, a spinning top, heck, a whole planet. It feels like that's got to be a totally different kind of physics, right? A whole new rule book. But what if it's not? What if it's the same rules, just in disguise? All right, let's get into it. The big idea here is to think about rotation as a different language. It's not a whole new science. We're just learning a new set of words to describe the exact same physical principles we already know from straight line motion. And this is basically our Rosetta Stone, our cheat sheet for translating physics. Look at this. For almost everything we talk about in linear motion, there's a twin in rotational motion. Position? Well, now it's angular position. Velocity becomes angular velocity. And you see the big ones down there? Force, mass, momentum? Yep, they all have a spinning counterpart. This table is going to be our guide for this whole thing. Okay, so let's try our first translation. We know that to get something moving in a straight line, you need a force. Simple enough. So what's the thing that gets something to spin? That spinning force has a name. It's called torque. And it's not just a simple push or a pull. It's a twist. The best way to think about it is opening a door. You don't push right next to the hinges, do you? Of course not. That's way too hard. You push on the handle, far away from that pivot point. That effective turning force you're applying, that is torque. All right, now let's pull out a classic. We all remember this one from school, right? Newton's second law, F equals ma. Force equals mass times acceleration. It's like the most fundamental rule of how stuff moves. You apply a force, a mass speeds up. Done. Okay, now look at this. This is the rotational version. Just look at it. The formula has the exact same shape. It's incredible. All we did was swap out the words from our dictionary. Force got replaced by torque, mass got replaced by something called moment of inertia, and regular acceleration got replaced by angular acceleration. It is literally the same law, just spoken in the language of spin. Okay, so we just swapped mass for this new thing called moment of inertia. But what is that exactly? It sounds kind of complicated, but it's actually super interesting. It's more than just a mass for spinning things. So here's the deal. Mass tells you how hard it is to push something in a straight line. Moment of inertia, on the other hand, tells you how hard it is to get something to spin. If an object has a really high moment of inertia, it's tough to get it rotating. And once it's going, it's really tough to stop. And this is the part that's so cool. With mass, all that matters is how much stuff you have. But with moment of inertia, what matters is where that stuff is. It's all about the distribution. Go back to our ice skater. When she pulls her arms in, all her mass is crunched up close to her center. That's a low moment of inertia. But when she stretches her arms out wide, it's the same amount of mass, but now it's spread out, giving her a much, much higher moment of inertia. And guess what? This whole translation thing, it just keeps going. It doesn't stop at forces and mass. It works for the big concepts too, like energy and momentum. The pattern is just everywhere. Take a look here. On the left, that's your classic kinetic energy, the energy of motion, 1/2 mv squared. Now, look at the right. That's the energy of a spinning object. Do you see it? It's the same pattern, 1/2, but instead of mass, we have moment of inertia, and instead of velocity, we have angular velocity. We literally just translated the formula. And no surprise, it's the exact same story with momentum. Regular old linear momentum is just mass times velocity, so its spinning twin, which we call angular momentum, is, you guessed it, moment of inertia times angular velocity. And let me tell you, this idea, angular momentum, this is the one. This is the key that unlocks that whole ice skater mystery. Okay, this is it, the big payoff. We're going to take all our new translated words, torque, moment of inertia, and especially angular momentum, and we're going to put them all together to finally understand the secrets of the ice skater's spin. The whole secret boils down to one simple, incredibly powerful rule: the conservation of angular momentum. All it means is that if nothing from the outside is twisting you, your total amount of spinness, your angular momentum, cannot change. It's locked in. It has to stay constant. Period. Okay, let's walk through it step by step. Step 1. The skater starts her spin with her arms stretched out. We know what that means, right? Her mass is spread out, so she has a big moment of inertia. Step 2. She's spinning on smooth ice, so there's basically no outside torque. That means her angular momentum is now conserved. It's a fixed number. It can't change. Step 3. She pulls her arms in tight to her body. What does that do? It brings all her mass close to the center, so her moment of inertia suddenly gets way smaller. And now for the finale, step 4. The universe says her total angular momentum has to stay the same. So if that I part of the equation just dropped like a rock, the only way to balance the books is for the spin speed part, the angular velocity, to shoot through the roof. And that's it. That's the secret. She spins faster because the laws of physics demand it. This really just says it all. It's a cosmic trade-off. If you change how your mass is spread out, your spin speed must change in the opposite way to keep that angular momentum constant. The universe is a very strict accountant. And look, this is way more than just a cool trick for ice skaters. This exact same principle is working everywhere. It's how a diver tucks in to spin faster for a flip. It's how a gymnast controls their twists in the air. It's how giant flywheels store energy. And it's even how satellites stay pointed in the right direction without firing their engines all the time. This law is truly universal. So think about what we just did. We didn't learn some crazy new physics. We just took what we know about straight lines and found the right words to translate it into the language of spin. And by doing that, we unlocked one of the most fundamental rules of the cosmos. Angular momentum shapes everything, from how planets orbit the sun to how tiny electrons behave. It really makes you wonder, what other secrets are just waiting for us to find the right way to translate them?